Welcome to our 10th lecture on solar electric energy systems. Today we'll talk about durability and quality of PV modules. So we encounter tests, different problems that can occur at PV modules and the countermeasures. In particular, we will discuss microcracks, lamination issues, and PID, that's for potential-induced degradations. So what tests do we have to encounter that? There are the so-called standard IEC tests. So this is usually performance after some stress, some mechanical, thermal or electrical stress. We have the IEC 61215 for crystalline silicon, and for thin film modules the 61646. For safety, there are additional tests, the 61730, or which is very equivalent or very, which is very similar, the UL 1703. Additionally, we have non-IEC tests that covers issues that are not covered with the IEC tests. So these are special purpose tests, for example, for extreme sites, salt tests for seashore locations, sand tests for desert locations, ammonia, which escapes from farms, for example, pig farms, or untypical loads. For example, some locations, they have enormous amount of snow or heavy hail. Then we have newer tests, a multi-purpose test, or combined loads. Let's first take a look at the traditional IEC 61215 tests. So we and additionally also the IEC 61730 tests. In this graph you see the IEC 61215 test in blue color and the 61730 test in yellow color. While it's very small here, I just give you a zoom on that. So you have here the upper part of that test schedule. First you have to get 8 modules or 7 modules and 1 laminate. What you do first is so-called preconditioning. So you apply an irradiance of 5 kilowatt hours per square meter. Remember, just as this is about equal to 1 summer day in Germany. In winter, that's rather difficult to perform this test because we often have irradiance values of only half a kilowatt hour per square meter. So we have to wait for 10 days. This is to check whether, especially at thin film modules, there are some degradation issues, and then you want to at least not eliminate them, but keep the modules at the same level. What happens then is the so-called visual inspection. That means that you check the modules for visually apparent issues, for example, bubbles in the laminate, cracked surfaces, cables, terminal box issues, and so on. Then you make a report about it, and then it comes a more important test, the STC power determination. So you measure the power output of the PV modules under standard test conditions. So you apply an irradiance of 1000 watt per square meter with a spectrum of AM 1.5 at an operating cell temperature of 25 degrees. You have to take care during the test that the module isn't heating up during that test, so otherwise you have to compensate for that temperature. Usually what you do is having flash tests, as you would take only not a permanent light source, but a flash light source. This is also more easy to perform the necessities for the AM 1.5 spectrum. For permanent light source, that's quite difficult to achieve. For flash, that's much easier. What you do then is the insulation tests. Come to that a bit later. So this is dry insulation tests. You apply a voltage that's much higher than the usual system voltage. What you do then is a wet leakage current test. So the module goes under water, and then you measure the leakage current and the resulting resistance of the module. Additionally, for the safety test, the IEC 61730, you do a fire test here and module breakage tests. Usually it's no issue, the fire test, because the materials don't burn a lot, but it's required, especially if you want to integrate the modules in the housing construction. Also, a partial discharge test is a very high voltage, and you with a voltage that usually allows a discharge, so you're breaking the insulation there by the very high voltage. Conduit bending tests, that's usually not required in Europe, but for example, in the United States, the cables are usually in a conduit, it's a tube, and you test the durability of that cable tube. And a terminal knockout test, so you test the knockout force of the terminal box. Then the modules tests are getting separated, so you put one module, call it outdoor test, you put it here, the roof, and you measure the temperature coefficient, so you measure the temperatures and take a look at the current. At the same time, you have to monitor the irradiance and especially the voltage. Is the voltage how much is the voltage loss during a temperature increase? And then there's outdoor exposure tests. It's usually irradiance of 60 kilowatt hour, so more than 10 times more than the preconditioning tests. Sometimes that's not possible in the winter time in Central Europe to perform this test, because it would have to wait for many weeks to perform that. And then you see there's a small rectangular here, 10.1, 10.2. That means you again carry out the 10.2 test. You do again a visual inspection and see whether something is happening, whether something is broken or some extraordinary issues occur then. And then you do the MST 16 test. That means you do a dry insulation test after that. Then you do the NOCT determination. That means the nominal operating cell temperature determination. That's, as we discussed already, that's at an irradiance value of 800 watt per square meter, a module elevation angle of 45 degrees, a wind speed of 1 meter per second, and you take a look at the resulting temperature. If you're not reaching exactly that value, there's a compensation table for that in order to get those values, and then you go on with the STC and NOCT performance. Then additionally, quite important, the performance at low irradiance values, especially in Central Europe, the probability of having such low irradiance values in the vicinity of 200 watt per square meter is quite high. Therefore, it's quite good to have data on that irradiance value. Then you carry out a bypass performance test. Also, again, as you see, they do again a visual inspection, STC power determination, and the dry insulation tests. Hotspot endurance tests, so you shade artificially one cell to different values, so just to 50%, 75%, and so on, to find the maximum stress of that of the module. And then you carry out also the sequence of tests, plus additionally the MST 16, that's the wet insulation tests. Then a temperature test and so on. Let's go back. Then is one module, is just a control module, you keep it. This is also, if later is happening someone and there will be some juristical problem, you always have a reference module which is totally untreated. Then you have two modules where you apply the ultraviolet preconditioning tests. That means you apply a high dose of ultraviolet irradiance and see whether something degrades visually, but also in terms of performance. And then you do an insulation test, and UV is also quite an important test because some of the materials, they degrade at ultraviolet radiation, principally the backsheet, but also been reports about non-stable EVA equipment, so the EVA degrades and gets colored and therefore reduces the power output. This is tested afterwards again with the STC test, and the visual inspection, and also the insulation in kind in case some of the materials get brittle, and you check the insulation again. Then you do a thermal cycling tests. So you put it in a climate chamber for 50 cycles. The temperature is between -40 and +85 degrees. And you cycle it for 50 times and see whether something happened to the modules, and test the performance again after that. Then you see here there's a humidity freeze test. It's also, the module is called cool down up to -40 degrees. But you don't control the humidity, so it takes the humidity from the higher temperature, and at the lower temperature this humidity cannot be supported by this cold atmosphere anymore, and it starts to condensate on the module and it turns into ice, and even in small pores in the module there you have ice, and this is a really harsh test on the module. You only do it 10 times. It also requires quite expensive climate chamber to carry that out. Then continue that a little bit later when you come to the second part here, and then you have two modules where you carry out the damp heat test for 1000 hours, so that's a temperature of 85 degrees at a humidity of 85%. That's usually also a test where you see a lot, but it takes a long time. 1000 hours, that's more than 1 month. But then you see some results, for example, in delamination or in insulation tests. Therefore, you carry out the performance test again. At first a visual inspection, then the STC performance test, then the insulation dry and wet. Then these two stress modules are stressed again. One is checked at the hail impact test. So you do a hail impact on 11 points of the PV module at a speed of 25 meters per second, and with a diameter also of about 25 millimeters. There's a table for that. If you vary in size, you have to adjust the speed and so on. And again, you check the module visually. Sure, if you see visually also there's cracked and so on, that's quite severe. And then you do the STC performance test and an insulation test. In parallel, you perform a mechanical load test on the module to simulate wind loads or heavy snow loads. Usually the load is 2400 Pascal, but for heavy load conditions, for example, if you install a PV module in the Alps, then an enhanced test could be carried out, which is carried out at a mechanical load of 5600 Pascal. Again, you perform the different performance tests after that stress. Then there is a thermal cycling test. It's the same as this test here, but this time with 200 cycles. So it's also quite severe tests. As I told, the temperature starts from -40 degrees and goes up to +85 degrees, and that's repeated 200 times. Let's go to the second part. This you see here. We were here at the humidity freeze test. So this test you already have. So you have here additionally for the first row the robustness of termination tests. So you just check what force you can apply to the cables and so on. Again, they put all modules to the wet leakage current tests, even if they performed already a dry insulation test afterward, but then you already all test them for the wet leakage test. Even the control module is tested for that. That's not really a stress. You just check whether the insulation is sufficient. Then there are some additional tests here. Here cut stability tests. So you test whether when, for example, the electrician applies a knife on the back sheet of this module, whether the module survives it and the insulation is still given after that. So this is more, as I tell you, the yellow tests are more safety tests, the accessibility tests, whether you can take an electrical shock, which nowadays is less a problem, but when you have open contacts and so on, this can be a problem. Pulse voltage tests goes up to 8000 volts, and pulse voltage is applied and so on. Do a test, and then do a visual inspection after that. Here also a temperature test and a reverse current overload test, and then just a wet insulation test, and then a visual inspection. Then you go to the end. The requirements are you are not allowed to, after all tests, to lose more than 8% of the STC performance. After each single test, it's not allowed to lose more than 5% of the STC power. So again, these tests here. For thin film, this is a bit different, the IEC 61646. This is takes care on the problem with the STC measurements, because these thin film modules they sometimes have reversible degradation, and first you have to put them on a certain level, so you do some light degradation with them before each single measurement of power, and that takes a long time, and therefore you leave out some 10.2 tests, that means STC power determination tests for the thin film modules. You see here the so-called light soaking, to do light degradation in order to find out the actual power of a thin film modules. These are typical failures after such IEC certification. The statistic is by TÜV Rheinland here. No, this is PI Berlin. So you see here the damped tests is usually quite critical. Humidity freeze test, as I mentioned already, mechanical load test, and light soaking tests. And here you see the according values of the test failures, what happened to them. This is for thin film modules where the standard IEC 61646 is applied. And for the crystalline modules, you see the most critical is the damped test and the thermal cycle test. Here you have the highest failure rates here. Let's take a look at the entire value chain of a PV module. So we have the raw materials. There could be also already some quality problems. For example, inhomogenities or impurities of the raw material. There could be some damage during sewing or handling of the wafers later on. And the transport of the wafers to the module factory could already pose some problems. Then you may have some problems if you go a step further at the handling of the cells, the microcracks that occur at the handling or at the soldering, then at the lamination. So various issues, for example, the temperature cannot be right, or the temperature distribution within the laminator could be could be too high. The pressure of the lamination could be different than required. Also, the duration of the lamination could be wrong. Also, what could happen are too small distances of the cell, which reduce the maximum voltage, the maximum system voltage, or the distance from the cell to the frame, or the diodes or the terminals. Then during transportation, it could be some issues with inappropriate packaging, incorrect declaration. This happens sometimes to declare higher values of some electrical parameters, in particular the power output. So you have to check that before, or at best at the end, and do a full performance test then. Stapling and storage, there could be some issue that there's a mishandling there. And vibration and hits. So if you transport it on a bumpy road, then it could cause some microcracks in the PV module. Then during installation, there could be also some problems during unload, unpacking, the treatments during installation. Usually there's a high cost pressure at installation, and people are paid on the number of installed modules, and so they treat them not very carefully. faults in electrical installation. Many of the installers don't have appropriate electrical education, and they, as I told you, the cost pressure is quite high, and they do it very quickly, and there could be some issues in the correct installation, or in a number of modules in series, in the kind of connecting them together, and so on. And mounting also could be some issues if the mounting foundation is not really fitting to the modules and so on, and so you put it into the frame, into the installation frames or in the foundation as a high mechanical pressure and so on. It could lead to some damage of the PV modules. And operation could be also stress from mechanical side, thermal side, UV side, depending on the location. For example, if you put it in the desert and you have a high temperature difference between day and night, this could lead to some extraordinary test stress. Or ultraviolet radiation. We just recently carried out some tests in Bolivia. There the modules are installed in an altitude above 4,000 meters above sea level, and there the UV stress is extraordinarily high. Interconnection, this is also an issue to the grid. So-called snail trails, found out that's usually microcracks which are propagating, and then they call a visual damage. Vandalism, theft is in some countries, or even in Germany, sometimes an issue. So you have to make sure that the modules are not stolen and so on. And last but not least, the hotspots and PID. The underlying issues I will discuss more in particular. So that's PID, the microcracks, and the lamination. First, let's see what is microcracks. These are cracks which are not visible. So you have to use a tool. This tool is called Electroluminescence, or short abbreviation for it is EL. What you do there is you apply a reverse voltage, accordingly a reverse current at the PV module, and make that visible. Usually do it during nighttime to not be confused by the actual solar irradiance. And the module starts to illuminate, starts to operate as a light emitting diode, and you have an infrared LED then, and you take a picture of that. And while physics is usually reversible, the locations or the parts of the PV modules which work well in the photovoltaic mode work also well in the LED mode. That means the bright parts, they are quite good, so this is working well. The dark parts, they don't work neither in the LED mode and neither in the photovoltaic mode. This infrared glowing is made visible via near infrared cameras. Actually, you can use any kind of camera. You just have to remove the internal infrared filter, and then you can make that visible. Here you see second part is already a heavy damaged module. For example, during transport, it looks like real transport because it's in the center, and then during transport, the center part is moving up and down, and during this journey, many cells have been heavily damaged. While all cells are interconnected in series, the most damaged cell is determining the overall performance, at least of the strings. If there are bypass diodes, if there are no bypass diodes, it's determining the performance of the whole module or even of the whole system. Take a look, there's a small movie about that. Oh, sorry. Here is actual live video, so you can see the breaking of the cells here live. So this is all the microcracks. I told these are microcracks because they're not visible really in the actual picture. And if you release the cells, sometimes you cannot see the microcracks anymore. What you do is carrying out a classification of the microcracks. So your first perfect model, just this is because it's a multi-crystalline model. You see some dark spots, but it's not really an issue. This is usually the boundaries of the multi-crystalline material, so that's perfect. Then you have some non-critical tests, so you see that's only the areas which are really dark are really small, and therefore the overall performance is not really affected. Then you have some critical issues. So here you see this part is completely insulated from the rest, so it's photovoltaically dead. And a series here you see a really large part of the modules are really dead and hinder the current flowing through that cell. So it's an issue where you locate the problems is also who is responsible for it and who is to pay for that. And this we try to distinguish now by this slide. So the relevance for the manufacturers, the buyers, retailers, installers, and investors. So that depends on the location of the occurrence of severe microcracks. So first at the manufacturer, then after the modules get delivered, you do usually STC performance tests, and this will happen, and this will reduce then factory output. So this is just the costs are at the manufacturer there already. This is a direct financial loss for the manufacturer. So if you have 10% cracks and you have 10% less output, then this is directly affected to his returns of the factory. Not so relevant for the buyers, because usually you buy modules as standard test conditions, the number not per square meter, you buy them in terms of power output. So if you buy 1 megawatt, you usually have the warranty by the manufacturer that you purchased 1 megawatt. And if there are damage, you get more modules for 1 megawatt. As you saw in the video, there is further reduction possible. So some microcracks only are visible only during the stress, and then they disappear, but later they appear, for example, during operation. Also, there can be some propagation of cracks, for example, that occur during further stress during transportation or installation, for example. Could be also happen some damage during transport. So you purchased your module with with a warranty of, for example, 1 megawatt, but then during transport something can happen to the modules, and then you get a power which is lower than the nameplate power. This is sure relevant for the buyers and the installers. So for them, it's then a direct financial loss during installation. So then also the actual PV power gets lower than the nameplate power, and it's relevant for buyers and installers because it's a direct financial loss. And during operation in the field, then the energy yield could be lower than expected, and this is particularly relevant for buyers and investors. There's a direct and indirect financial loss, because indirect because there could be an increased risk of hotspots and so on, which not causing directly damage but may reduce lifetime or so. Let's go for the first cause, the mechanical stress during cell and module production. So as I already mentioned, there could be some stress during soldering, so the interconnection of the solar cells. We see some typical issues, so these are repetitive black areas. So this is an indicator that happened during production. And So the cells are less reliable inside the module, and here they could lead to hotspots at reverse current on the field. During transportation, as already mentioned, so you have here high amplitude in the middle of the modules when you store or transport the modules horizontally, and here these cells are damaged after transport. If you have thicker cells or more rigid module construction, this may not appear, and you only have a little damage here. Here you have some black areas. These appear to be from the manufacturing, for example, during soldering and so on. So these are some examples carried out. So here is the breakage rate. Red is a high breakage rate. The 0 is non-breakage and so on. And here you see if you have a cell with lower thickness, then the breakage rate is usually higher. But as I mentioned, it depends also on the rest of the encapsulation, on the glass thickness, on the thickness of the EVA, on the frames and so on. But this is just an indicator here. And here you see the number of cracked models here. So the different internal mechanical tensions cause different breakage rate in the module. So thicker cells tend to be more robust. Here you see also the breakage rates, as I mentioned already, during transportation and transported horizontally. The modules tend to break more often in the center of the module. Could be also some issues in the lamination of the modules. This is a picture taken already in 2002. Nowadays it's a bit hard to take photographs in the manufacturing sites, so it doesn't look like this anymore. The parameters relevant for the reliability of laminations are, so you have to make sure that all the components are really clean, because it's like a gluing process. So the pre-treatment and the cleanliness of all solvers involved in the lamination process are relevant. The conditions of the EVA prior to the lamination process is really relevant. Because there could be the usable lifetime is gone, or storage conditions could be very bad, or some oxidation already occurred on that material. This could lead, for example, to some evaporation of the solving agent, and so they already appear to be laminated before lamination actually, and also there could be quality issues at the supplier already. Then there could be some issues during the lamination process, the so-called curing. As I mentioned already, the temperature or the temperature distribution in the laminator, the duration of the lamination could be wrong. Usually they shorten up the lamination in order to save costs, and therefore the model is not completely laminated. Also the pressure could be wrong. As I mentioned, also not only the temperature distribution, but also distribution of the pressure. If you use a very low-cost laminator, then there could be some high pressure in the middle, but less pressure on the sides, or vice versa. Check for lamination, quality check for lamination. So what you could do, which shows very good the lamination is carry out the damp heat test, the damp heat treatment for 1000 hours at 85 degrees Celsius and at a humidity of 85%. The disadvantage, it takes a long time. As I mentioned, more than 1 month exactly. It's 41.5 days for that test. What you can carry out is to check the condition of the polymerization of the EVA. So it's a chemical analysis, and it could be unsatisfactory anyway, because the EVA of prior to lamination could already be kind of laminated due to wrong storage temperatures, and then it appears to be good laminated, but actually the lamination could be of a very bad quality. What you do is usually to check the GALE content values, and this we find out now, usually. So in order to overcome this, there could be a destructive test that you really measure the peel-off force of a layer of the laminate in order to find out the actual quality. So this ensures really whether if the peel-off force is too small, then the surface could be either bad or the EVA could be either bad. So this shows all, but it's destructive. First, let's go in the gel content test. Could be some problems with the laboratory. I'll come to this a bit later. So you see first after a certain amount of tests how much the gel content is. So here, if you only carry out 100 cycles, extraction time, it appears to be quite good, but at the end you see that the gel content is very low after you carried out a sufficient number of cycles. So in order to save time and costs, some factories or laboratories, they shorten up that and just show the results after 100 cycles. But here you see if you do carry out a sufficient number of cycles where the gel content stabilizes, you see that these samples are really bad here. They're sometimes not visible. Here is this peel-off test. So you cut the back sheet on the module into straps and you measure the force. So here you see the back side of the solar cell here, and you measure the force here. It's changing a bit, but you take some average values on that, and this is an indicator for the quality of the lamination. We come now to PID, the potential-induced degradation. Tests, measurements, and countermeasures for that. Here you see such a model array affected by potential-induced degradation. So you see here these modules in the electroluminescence pictures, they look quite good, but here you see some complete strings which are completely dark, and that means they are not producing any power anymore. This is usually a function of the electrical potential versus ground. So the higher the voltage, the more damage is there. So these are possibly close to grounds, and this here are applied to a higher voltage, and there occurs a degradation. And here at the same model string, not, because they are closer to ground voltage level. This issue hasn't been so well known as the decades before. It's getting a growing relevance because of the increase of the system voltage. While formerly the system voltage has been limited to 600 volts, it's now 1000 volts, and even will increase to 1500 volts or even 2000 volts. Also, there's no galvanic separation anymore between the model array and the grid. Formerly, this has been given due to the transformers inside the inverter, and nowadays more cheaper and quite efficient inverters, they don't have any inverter anymore. Also, there is a tight yield optimization, so sometimes there could even have been some PID, but it hasn't been discovered. And nowadays the operators, they take a close look at the actual operation performance. So as I mentioned already, the decreased performance depends, or the PID depends on the module closer to the negative pole. So here you see the effect. So we have here positive and negative here, and the grounds, the module frame is grounded. And here you see an internal electrical field, not only from the NP junction here, but here from the inside the modules due to the high voltage applied to the system voltage. And these create also a reverse electrical field inside the cell, which is reducing the power output. And this is caused also the transport of ions from the glass is caused by that internal electrical field due to the high voltage, and they reduce the electrical field of the PN junction, and therefore reduce the performance of the PV module. So conditions for PID in the field is a high external potential, so high voltage versus ground potential, depends on the specific system configuration. There are climatic and weather conditions at the installation site. So we have a high relative humidity, a high temperature, and that leads to high leakage current in the field and the module levels. And there are some modules which are susceptible to PID, and this depends on the solar cells and the module design. As I mentioned, some issue is the accumulation of sodium ions from the glass to the cell and its interaction at the PN interface. The factors are all the system configuration, the actual weather and climate, and the construction of those modules. Some of them are really PID susceptible. Here we see some examples here. So we have here the same conditions, the same durations, 0 to 100 hours, 3 times. We have also the same negative voltage applied to minus 1000 volts, same temperature, 25 degrees, but you see here a strong dependence on the humidity level here. Here we have a very dry atmosphere here, 0% of relative humidity, and here we have 50% humidity. So you see here already some cells failed due to that PID effects, and here we see at 100% humidity, all cells failed due to this PID effects. Also, there's a temperature dependence. So here, if you have 25 degrees only, then after 48 hours only here, you see a relatively small power degradation of 3% only. If you have high temperatures here at 85 degrees, you will see a very significant power degradation of 95%. Here you see, as I already mentioned briefly, the transport of the sodium ions to the cells are responsible for that due to this electrical field created by the system voltage. Here is our PN junction, and this is the field applied by the external voltage, and these create the movement from the ions into the PN junction and the reduction of current and power. And this is causing kind of shunt behavior. So it's comparable. So this RP, this parasitic resistor, as I mentioned already, if you have impure materials, and therefore is reducing the performance, especially under low light conditions. You see this degradation at different levels in order to standardize a test procedure, because each test lab formerly had its own procedure. There is a now it's developed. Before it has just been a working group, and it's called IEC 62804-1, and this does carry out some tests, this define temperature and so on. Show you these parameters which are responsible for that tests. So one parameter is anti-reflective coatings. Nowadays we mostly have silicon nitride. This is a key factor, and not only silicon nitride only. It depends on the applied refractive index, the conductivity of the silicon nitride, and you see here the PID effect. If you have a low refractive index of the silicon nitride applied, then a PID is sometimes higher, not all the time. Here it's a bit higher, but not very much. If you have a relatively high refractive index of the silicon nitride, then there is no PID. It's quite interesting issue, but it's, as I told you, it's not at all conditions. So the idea is to avoid the accumulation of sodium ions at, above the PN interface, and this also can be carried out by the module encapsulation area. So if you use materials with higher insulation or intermediate foils for that, you can also avoid PID. for example, polyethylene or something like this. This is here you see the effect, and by that you can avoid the PID. So here you see the red part here. This is a very high insulating material, and then you can avoid the movement of these sodium ions. So summary, you can PID can be avoided on the module level. So that's the idea is to avoid the movement of the IED ions towards the cell, and you use a high insulating material to avoid that effect. So you can avoid a sodium-free glass or the encapsulation, a high insulating encapsulation, or in particular EVA material or other materials. Also, you can do something via the system configuration. So as you saw in the first picture, the PID effect strongly depends on the position of the module in the string. So you see here if the module here is close to the negative part here, where you apply a negative, so you have here the green line here, PV plus grid. So you have a strongly negative voltage, and this reduces here the power significantly. If it's here at number 10 about, then your voltage is quite low here, and so there is no PID effect. This could not only happen at crystalline modules, even the CIGS module are susceptible to PID. You see here the effectiveness of PID at the CIGS modules. So you see here degradation of 20%, of 80% if you apply this condition at -1000 volts and check it for 68 hours. If you do a reverse voltage, there could be also even some PID effect here, but degradation is much smaller, it's only 30%. So this is a typical test procedure. So you do initial measurements, check the do an electroluminescence analysis, most important the power output measurement, and then here you apply a voltage of -1000 volts. Have a humidity of 85%, do the grounding of the frame, and you check it for 48 hours. And then again, you carry out those measurements, power output and electroluminescence analysis, and then you do a categorization of the module. So if you have a power loss of less than 5%, so the module is prone against PID and yes, it gets a Class A certification. If there is some degradation here between 5 and 30% power loss, it gets a Class B certification, and Class C is for a degradation higher than 30%. Luckily, this effect is reversible, so you just have to get the ions back into the glass, and this you can do by applying a reverse voltage. So you apply, instead of negative, you apply a positive voltage. During nighttime only, you don't want to do it during operation, so you apply a positive voltage during nighttime. You don't need a lot of power of that, you just need basically a voltage source to do that, and then you can lift that potentials here up to avoid this negative potential, and then you reverse that effect. What you can also do in the system level, that you ground the negative pole. This is done formally, but nowadays with the modules which are not anymore separated galvanically from the grid, it's often not possible in such a system. So this hasn't been a problem formally, because transformers have been applied, and also the grounds have been, the negative pole has been grounded. Nowadays it's a bit problem, so there could be some quite significant negative voltages there. Here you see the effect of the PID recovery. So here first you see here PID, so you have the negative voltage of -1000 volts, and you see the strong PID effect of -60%, and then you apply a positive voltage, and you see immediately here the recovery. okay, it's 250 hours, quite a long time, so you have to use many nights in order to apply this voltage in order to get a recovery. You see it after some hours, there's already some recovery after some hours already. It's really at a really high temperature at 100 degrees. So the summary, PID can be stopped and reversed. Avoidance, stopping of negative potential. Alternative, you can do that, apply a positive voltage, basically during nighttime. Generation is possible at a suitable system configuration. Degree of degradation depends on extent and conditions. And here we see some effects. So here from the voltage current curve here. So you have here the model with PID, and here you see after 96 hours of recovery, the blue line here. So you see some not so much at the current and the voltage, but here you see the form factor is significantly the fill factor is significantly better, and this leads to higher output, or output which comes close to the original power output. So what we can do, we can do tests for PID, tests of reverse PID, and these methods to do that is either this IV measurements or the EL measurements, which you see on the top, but also infrared measures, so the recovery of the model. So this was a damaged model. Here you see, and now you see after generation, it looks much more homogeneous. Okay, we come to a different chapter. We talk about the challenge of quality and reliability in the situation in the PV market. As I mentioned already, there is a very hard cost pressure to not only doing installation, but also for the manufacturer. And so they quickly changed suppliers. Formerly, they used the suppliers for a long time because there was trust and so on. But nowadays, while you always have to choose the actual cheapest supplier, there is a high fluctuation between the supplier. Sometimes the quality and the suppliers are unknown. Usually you have, if you change the supplier, you should carry out a recertification. So you have to, as I mentioned, the IEC 61215, you should carry out the whole certification once more. Or if you have a recertification and do only little modifications, you have to at least carry out some of those tests. This is given by the certification body. So it says, okay, if you change the glass material, you have to repeat a sequence of tests, and so you make sure that the buyer of such modules receives the same quality. But sometimes this does not happen, so the manufacturer are really cheating there. So they keep the same certificate, but the module is different. Often these manufacturers are in China and so on, and it's quite hard to have access to the supplier, and that's is an additional problem here. Yes, this practical quality problems in the field are now playing an increasing role. Just I mentioned these different issues, microcracks, because also the cells get, the thickness of the cells is getting smaller, and this causes more microcracks, or this problem with PID due to some saving in the system configuration. So you don't have any transformers anymore, you don't ground the frames anymore, and so on. And also, as I told, this reduced lifetime due to bad lamination or to bad treatment of the lamination components. Here we see a smart movie again.
This movie has been showing about how to carry out this EL inspection, not directly at the module level and by dismantling the modules. You can carry it out also via drones, which is to apply a reverse voltage on the modules, and you see in the nighttime you see the modules glowing, and then you take infrared picture of the whole PV array. This facilitates a lot because you don't have to stop operating the power plant, and you don't have to dismount the modules you want to test. There's even now a method being tested that you can do it during daytime. So you do a login inverter, so you just apply for some moments reverse voltage, and you see by the fluctuation of the infrared radiation the EL picture, so you can extract it later from that. So just to give you a kind of summary, in order to carry out quality control, you have to check the whole value chain. So you have to start at the factory. So you have to carry out a factory inspection unannounced. So if you announce, people can rearrange the whole factory there, and then it's not the same quality that you get as a usual customer. And also repetitive. So if you once make a factory inspection and they are sure you only will come back in a year, they may change the suppliers. They may change the procedure of. As I mentioned already, so often the duration of lamination is shortened in order to increase the throughput of a factory and so on. And so this you want to avoid, and therefore you have to check unannounced and at high frequency. Also, additional tests can be carried out at the, before shipment. For example, in China, to have a small lab there and check. And for some customers, for example, the Japanese are really interested, so they even check the whole production, every single modules. But typically, to have the best cost-benefit ratio, you check about 1 to 2 per mil of the modules. That means about 10 modules per megawatt. Nowadays, 1 megawatt is about 3,000 modules. Formerly, that's been about 4,000 modules, depending on the module power. You don't have to apply full certification, this requires a long time and it's very costly. So you just combine some tests of them. Usually a price in the vicinity of 1% of the module price is quite acceptable, so to carry out such a quality control. Additionally, there could be some happening during transportation. So you do again tests at the arrival on installation tests and additional tests after installation. That means the commissioning of the system if you interconnect the PV system on the grid. And there's usually the customer there also and the utility, and altogether you initiate the systems.
Then you do some final performance tests. So you have a power meter, a radiance meter, and a cell temperature measurement, so you can find out whether the power given on the nameplate can be really fulfilled, considering sure the losses by temperature and maybe lower irradiance. Also, it's quite recommendable to do a performance test before the end of the warranty period. If there is some degradation and so on, you will still have a warranty by the installer or by the manufacturer. So we come now to the exercise of this quality lecture. So just carried out to the next exercise there, and I give the solution. So first question was, why is the test of some samples by the manufacturer to the test laboratory not sufficient to determine performance and durability of a series of PV modules? What has to be done to secure performance of quality of PV within a PV project? If you want to do a holistic approach, the lamination quality. Why is a GEO content test not sufficient to determine the durability of the laminations? What additional tests would you propose? A testing laboratory is offering all tests necessary for IEC 61 to 15, and they guarantee you that all tests can be carried out within a month. Is that possible, and why or why not? Fifth is, why is the PID issue become more relevant during the last years rather than a decade before? That's it. Thank you very much.